Well, dear students, now we are again back to the forging lecture. The technology of metal forming series. This lecture we are going to present and see the analysis of stresses and load for simple forging of a disc under plane strain condition. We would also see the little bit about the die design issues and the different types of forging again, and as far as the different presses are concerned, we would look into. So, to start with, let us look at this figure where we have a case of impression die forging. Simple one impression is taken, and this shows the schematic diagram showing the influence of fillet radius on metal flow during progressive stages of the die closure. As I told you, the die block may have different impression, and each stroke gives a impression. Last time we had seen, and as a designer there is a influence on the fillet radius provided to the impression, and the parting line that you are going to select for the design, die design. So, this figure shows. Now, look at, if the fillet radius is not proper, what is going to have? So, the filling will not take place. So, that shows a proper fillet radius, and another case it shows on the other side that the fillet radius is not proper or it is too small. In that case, there is a defect which we call as lapse. So, lapse will be a defect in forging is generally generated if the fillet radius is too small. So, that is how, and in the second middle figure if you see, the filling has not been completed. So, that is the another problem while the closure of the die happens. So, this is just an idea how the die designer takes care of these things. This table gives you an representative design guidelines for draft forging cases. So, as you know, the draft forging where you can use a power hammer or simple hydraulic hammer, and that may be pedal operated or may sometimes hand operated as well. So, generally a basic guideline is that number one, if you choose that the choice of the parting line, when you design the dies for draft forging cases, the dies, so the proper parting line must be chosen such that the parting line entirely happens on one die half. If it is up or down, that will not give you a good flow lines, and the strength of the forged component would also suffer. So, you can see here on the side a poor parting line and a good parting line has also been shown in the die motion. So, a proper die parting line must be chosen. Another, one must avoid non-planar parting lines. As you see, a poor parting line, that is a non-planar on the left side, right side is a better parting line, that is a kind of planar one. The third basic rule is that one must provide taper, because once these two dies, upper and lower dies, are too close and the filling has taken place, the forged component has to be taken out. So, if there is no proper taper, it would be difficult to take out the forged component either for the subsequent forging or for the final one. So, there must be there is a poor in the first case it has been shown as the poor taper, on the other side the correct taper has been shown. You can see the bottom one, it has got a taper. The other design care is that one must locate parting line so that metal will flow parallel to the parting line. If it is not parallel to the parting line, it is not a good design. So, that is how you see the first case gives a poor parting line selection in terms of the flow of the metal, whereas the second one is the better parting line. The other case where the design for the parting lines at almost half of the height must be taken. Say you select the parting line such that if the workpiece is not very complicated, so let us have a parting line which covers half of the workpiece. If it is very low or very high, that does not represent a good design as far as the flow is concerned, as far as the flow lines in the forging is concerned. So, if you look at the poor design is that shows the parting line is slightly below the middle portion of the forging, whereas the second, which is a better design, it is in the almost mid of the part. Another guideline is that one must avoid sharp corners, sharp changes in the cross section as well, and cross section that project progressive abrupts in the die. So, if you look at the first case is the poor one, where it shows a projection, a improper projection, and in second case which is a better design. So, that way there is no sharp changes in the cross section. So, that has to be taken care, and the other guideline is that one must avoid excessive a kind of section like this. So, thin section should be avoided, very thin section, either you take it on one side of the die, but it should not be the parting line like that it comes to the very thin section, because that creates problem in filling the die. So, the left side, if you see the poor design in case of the thin cross section is concerned, and the better design is that you avoid it. So, that is how the this slide shows you some of the guidelines. Now, if you do not follow these guidelines, see, this is what is the parting line and the effect of the flow lines. These flow lines, as I told you, it is directly concerned with the strength of the forging. See, the first case where the A part, the parting line is taken as the bottom one, and because of when the filling is taking place, there is a filling very, it is not non-uniform, and the metal flow lines that and the grain structure is represented at the parting line therefore. So, there must not be any unfilled section. So, a proper parting line is that when it is taken as the middle one. The other case, other figure, if you see, the most economical, as all of the impression is in one die. So, that is also a very good example, because the flow lines are then will be very uniformly distributed without any discontinuity. And the other, on the right side, if you see the flow lines, this particular parting line should not be above the center of the bottom web, if you look at. So, that is also a bad design. Now, another case, the fifth one that is chosen here in this figure, the parting line at the ends of the this particular top web, this results in a good grain structure in fact, and that is how either you take it at the one side of the die. So, one either top and lower, but when you choose the middle one or very lower position, so that should be avoided, and that is what the guidelines that we explained is going to tell you the effect of a proper parting line in terms of the flow lines of the metal. Now, let us look into the deformation, how it is going to take place in forging. If you recall the stress strain curve, simple stress strain curve, and if you calculate the work of deformation. So, if you remember in the very first lecture, the work generally is given by the force multiplied by displacement. So, in this figure stress strain curve, if you take a incremental strain, as I told you, so the incremental strain you can make use of integration to calculate the total strain. So, work can be calculated as the force multiplied by delta L, that is the incremental displacement, and if you calculate the work per unit volume, that is capital U, that can be calculated as F multiplied by delta L and divided by volume of the forging, because the volume can be calculated as the cross sectional area multiplied by the height or length. So, the per unit volume, work per unit volume can be simply calculated as stress multiplied by strain, and this strain in fact is nothing but the area under the stress strain curve. So, that is the work done work. So, the work done per unit volume that we calculate here is stress multiplied by strain, and that one can calculate out of this stress strain curve, where from 0 to epsilon 1, if it is chosen, the blue line that we have located here of incremental strain d epsilon. So, sigma multiplied by d epsilon, and from the range is from 0 to epsilon 1. So, that is the area under stress strain curve, and you can get the work of deformation per unit volume. And if you recall this equation number 3, as the earlier also we reported, so the stress is given by K multiplied by epsilon, that is the strain raised to power n, where K has been taken as the stress corresponding to the strain of unity, and n is the material constant. So, if you substitute this stress into the previous equation number 2, one can find out the work done per unit volume as this, that is K integration 0 to epsilon 1 epsilon raised to power n d epsilon, and that's gives you a value which is equal to y star and epsilon 1. So, y star is nothing but a k multiplied by epsilon 1 raised to the power n divided by n plus 1. So, this has been rounded because it is a almost a single unity that represents, and we, if you recall, the y star is termed as the average flow stress. So, for cylindrical shapes under compression, that we have already seen it. So, the total work per unit volume is can be total work then can be calculated out of this as volume of the forging multiplied by y star multiplied by natural log of h0 by h1, where h0 and h1 are the two heights of the compression, initial and after. So, this analysis applies to unidirectional deformation. In fact, for more general, where you require the multi axial deformation cases, the effective stress, that is the sigma star, is used in fact, and in that case the total work required for deformation involves two more components, as the work to overcome the friction because of the dies and all that toolings under which it is flowing. So, the frictional work done between the workpiece and the surfaces, and the another part which we call it as the redundant work. So, that arises from the difference between the ideal and actual deformation, because ideally we calculate without many assumptions. So, but when you actually do it, because of the limitations, this comes, and that is how we can say the redundant work as difference between the ideal and actual deformation. So, this starting with the work of deformation. Now, let us look into the analysis of stresses and load of deformation for very simple disc deformation, where we are going to use slab method and by simple compression of disc, and let us start with the height h disc and diameter we can say it as d. So, you know the slab method, we take a small element of if the radius is a of the disc and height is h. So, we can take out of this at dx of the dx strip, and at a distance of x from the center line of this case, and let us look into the different stresses that is acting on this particular element, which is shaded like here. So, if you look at, because there is a compressive stress. So, if I call it as sigma y, and the interfaces, the upper die and lower die two interfaces. So, if mu is the coefficient of friction, then that becomes your the force or the stress is nu sigma y, and because the force, the material is going to flow in this x direction. So, if the stress on one side is sigma x, so other side which is opposing one, which opposes the deformation, that is sigma x plus d sigma x, and that is how the deformation takes place. So, this is the force equilibrium onto this small element dx. So, looking into this, one can now write down the equation that is in x direction the sum of all the forces must be 0. So, the material element shows which is subjected to normal and shear stresses as shown here. So, shear stresses are due to friction and other normal stresses is because of the so the equilibrium of the element if you choose in x direction. So, sigma, that is the summation of all the forces on the element in x direction must be 0. So, one can then write down this particular equation, that is sigma x plus d sigma x multiplied by h multiplied by z plus 2, because 2 faces. So, 2 new sigma y multiplied by dx, dx is the element thickness that we are going to take, and multiplied by z, then minus sigma x multiplied by h multiplied by z, and this summation has to be 0. So, if you divide it, because the d is on the side, z is on all the sides. So, if you divide it by z, one can simply get an equation which is d sigma x plus 2 mu epsilon y dx divided by h, and that is what is equal to 0. So, this equation contains two unknowns, basically sigma x and sigma y. So, another equation is needed to solve the problem, because to calculate two unknown values there must be two equations. So far we have got only one equation. So, the second equation can be obtained from the yield criteria, as you know. So, one can use Tresca yield criteria or von Mises yield criteria, but we have already seen in the previous course that the von Mises yield criteria is better as compared to the Tresca. So, if we choose the von Mises yield criteria, and in that accordingly sigma y minus sigma x must be constant, and therefore it follows that d sigma y becomes equal to d sigma x, and if you substitute for the d sigma x value in equation number a previously, and that makes you d sigma y plus 2 nu sigma y multiplied by dx and divided by h, that must be equal to 0. Or simply one can get d sigma y by sigma y, and that is equal to minus 2 nu dx divided by h. And then if you solve this, so one can get sigma y, which is the compressive stress, that would be equal to capital C, which is a constant, multiplied by e raised to the power 2 nu x divided by h. It can be noted that sigma y is a function of nu x and h, and the value of C, which is a constant, therefore can be calculated by the boundary conditions. Like, the boundary conditions are such that the edges of the workpiece where x is equal to a, we have sigma x 0 and sigma y is equal to y star, that is the average value. Now, if you substitute in the equation number b this boundary condition, so one can find out the value of C. So, now if you substitute in the value b, one can get y star is equal to capital C e raised to the power twice nu a divided by h, and from this one can calculate the constant C, which is given by equation number C, that is y star multiplied by e raised to the power twice nu a divided by h. Now, if you substitute this particular constant C, which is obtained in equation C, and if you substitute in equation B, one can find out the equation. of the yielding compressive stress for that causes plastic deformation and that's the plain um, strain condition. Another assumption has been that the deformation is uniform deformation, it is at very slow speed and cold. This case we are considering at cold forging of this. So we get the equation sigma y which is equal to load in fact. So the one can say it as capital P, and that is nothing but equal to y star multiplied by E raised to the power twice nu A by H multiplied by E raised to the power twice nu x by H, or simply we can write down capital P is equal to y star multiplied by E raised to the power twice nu A minus x divided by H. Okay. So this is what one can then calculate as the normalized form, that is P by y star. If you take it the P by y star, so that is the normalized load, and and one can then write, so simply one can write down as P which is equal to y star E raised to the power twice nu A minus x divided by H. So the stress x one can find out as sigma y star, or stress x can also be written as y star multiplied by sigma E raised to the power twice nu A minus x divided by H and minus 1. So this can be plotted out of the equation D. So in a normalized form, as I told, the P by y star against x direction. So if you look at this figure, it is plotted up with the shape which is shown here. So workpiece, and at the center it is maximum, that is y star when x is equal to 0, and when x is equal to a it is minimum, you see there, and that is the variation in terms of the E raised to the power twice nu A by H. So the average pressure can therefore be calculated from the area which is under this particular plot. So an average forging load can be calculated, which is P average, and which is equal to y star multiplied by 1 plus nu A by H. This is the simplest form of forging of a disc under cold condition. So this is what's the this kind of calculation of load, and then one can also choose a proper motor for selecting a proper press or hydraulic press, so that the proper forging takes place without any problem. Another issue, as I told, is the formation of flash, because due to radial flow flash is formed, and the flash plays a very important role in filling the forging cavity in die forging. So two things are important as far as the flash formation is concerned. Number one, its A by H ratio is very high. If in case the A by H ratio is very high, such that it needs high pressure, this encourages the material to fill the die cavity. The secondly, during hot forging, and due to its high surface area, flash cools much faster, and thus it will resist the deformation. So these two things must be taken care. That means A by H ratio must be very high, such that it will require high pressure, and this will encourage the material to flow into. And when you carry out a case of the hot forging, so the high surface area keeping in mind that it cools faster accordingly, and that will create filling problem. So in that you go for the A by H ratio to be high for those surface area reason. Second thing, you can calculate the pressure calculation in the die forging, as pressure calculation is the somewhat difficult due to the complexity of the die cavity and the forging complexity of the shape complexity of a given forging. So because different sections are subjected to different stresses, strain and strain rates, so the pressure multiplication factor is generally used. So if you use a pressure multiplication factor as Kp, so you can insert this, that means force F becomes Kp multiplied by Yf multiplied by A. So where capital A is the projection area of the workpiece, and this Kp, that is the pressure multiplication factor, in a very rude manner as a thumb rule is taken as for the simple shapes when there is no flash formation we can take it as between 3 to 5. When there is a simple shape but there is flash formation, then this factor must be taken as 5 to 8. And if the shape, the forging shape is very complex and there is therefore the flash formation as well, so one can take the value of Kp as 8 to 12, between this range depending on. You can introduce this factor Kp with a shape complexity factor that we will discuss later. As far as closure of the forging is concerned, as I told you, if you look at the figure at the right side here, where the variation of required load as a function of the forging stroke is concerned, one can note the rise in the load after flash formation. You can look at there. The contact between the flash and die face is limited to an area which is known as a land. You can see here, initially when the forging energy, then the filled one, and then the flash. When the flash formation, it requires further heavy load, and then only the die will close. So that's how it shows. On the left side the same flash passes because it requires further pushing of the material under the cavity, and therefore the web side, rib side, fillet, proper fillet as I discussed, the corner radius, the trim line, the parting line, and that all affects the load required. And you can look at this figure, simulation figure, where the filling and upsetting are shown and the flash comes out, yellow one. This is another figure showing the simulation using some finite element packages. So finite element packages are very conveniently used now to simulate and design dies, etc., with a very accurate and very reliable manner. For the die designer, these simulation tools has become just like a calculator for quick solution delivery. So this is what's the flow line source for a case of when you have a proper die design. If the proper fillet and proper shape, that gives a very good strength, and no doubt you require the minimum load for deformation when the flash is going to start, and that's how the flow lines are concerned. So you can make a study with the flow lines as well as under slip line theory that we have already considered and explained. So usually, as I told you, you start with a blank. This case shows what happens to a forging, rather complicated forging, wherein you have a connecting rod, and so you start with a blank and then you do the edging operation. See, these all 5, say starting with blank, edging, blocking, finishing and trimming, these all impressions are there on one block, die block. And the yesterday lecture I had shown you a die block. So these shows the stages in forging a connecting rod for an internal combustion engine. Generally it is used. One can note the amount of flash that is necessary to fill the die cavities properly. You can see the edging, then the finishing, after edging the blocking, so the flash passes out in the nuggets, and then the finishing one, when the flash passes through all around and the whole cavity is filled completely, and then you can trim it and then make the other operations as explained earlier. This is what the stages showing. So you can look into the stages here, where starting with your blank and then edging, blocking, these one, and this the bottom one shows the simulation, FEM simulation. So when you perform FEM simulation by making solid models of these and solid models of the dies and the impressions on the die block, and you can perform it by FE modelers like deform and all that. So one can very well you design the dies with proper radius, underfills and all those things for parting line, and that's where you save the time. So this is what's the use. This shows another complicated situation where it shows the intermediate stages in forging of a crankshaft. Is much more complicated shape, wherein you start with the roll forged workpiece. These intermediate stages, which is 5 stages here, are important for distributing the material and filling the die cavity properly. So you start with a roll forged first pass, then in the second pass it goes to the second pass, which is roll forged, and third is the blocked in the closed die forging, as you know. So the proper filling takes place in the third stage, and the fourth where you have the finished forging in the closed die forging again. So this it fills the whole area, and then after the fifth one with the selected parting line you can remove all the flashes that has come, and that's what an example. This is the case we discussed so far to show you the role of a proper design. Usually different metals, different alloys we come across for forging. So there must be an idea how these alloys, as far as the forgeability is concerned, like you can there are alloys that are being forged: aluminum alloys, magnesium alloys, copper alloys, carbon and low alloy steels, martensite stainless steels, austenite stainless steels, titanium alloys, iron based super alloys, and there are further developments in hard and toughest material for forging. So like you have cobalt based super alloys, tantalum alloys, molybdenum alloys, nickel based super alloys, and very tough and light metal like the tungsten alloys. So if you look into the forging of these, so this slide shows you uh, the decreasing order of the different alloys as far as the forgeability is concerned. Forgeability means how easy you are going to forge it a particular. So the aluminum alloy, which is it is generally used in the range of 400 degrees centigrade to 550 degrees centigrade, and its forgeability is the minimum, so it requires very easy forging. Then next is the magnesium alloy, where the forgeability is 250 to 350. Copper alloys, it is 600 to 900. Carbon and low alloy steels, it is 850 to 1150. So this is what's the classification in the decreasing order of the forgeability. So the type, if you look at the last one, the tungsten alloy, its the value is 1200 to 1300, so very hard to forge, and the tungsten has a different metal, very light, very tough and hard, so forging becomes very difficult because it also reacts with open air oxygen, so you have to put certain kind of coating before forging as well. Like then nickel alloy, it is 1050 to 1200. So you can look at these, the order of forgeability. As I told you, apart from the proper parting line, selection of the radius, corner radius, and the gutter design and all those things, die allowances is also very important, the role of die design allowances, because you have to trim out, you may have to machine it after that, and because if the workpiece is hot, so after forging it will get, is going to shrink, so you have, but you have to maintain the proper shape and size with the proper tolerances. And also not only that, the whatever workpiece we are going to put, there has to be some allowances for work holding, so that you can put it, hold it properly with the toolings in the block. So basically we come across three die allowances, three types of die allowances. Number one is the shrinkage allowances, number two is your machining allowances, and number three is the work holding allowances. So these allowances are, one can select from a given database, the handbooks are there, forging handbooks you can use, depending on the size of the forging, depending on the temperature of the forging, and depending on the material that you are going to forge, there is a well documented information given in forging data book. One generally designer chooses from these document. These design data varies from one industry to another industry, and depending on the shape and size of the forging, one can, generally the designer chooses a allowances, so that a proper tolerances, shape and size is maintained as a good quality product. So if you look into the closed die forging, which is a very common one, closed die forging, where to produce different complex impressions. In closed die forging, when the situation, when there is no flash form, which is a simple case, and the material volume is generally calculated to exactly the filled die cavity, when the two parts of the dies are in contact. Okay, the process is also known in this case, when there is a no flash formation, we call it as a near net safe forging or production. So there is no flash formation, and the total cavity volume becomes the total volume of the workpiece. So the process requires, in this near net safe forging, requires high accuracy dies and is suitable for low load such as forging of aluminum and magnesium alloys, etc. But for very hard metals, we do not go for the closed die forging without flash. We always go for the flash. There are many other forging processes as I told earlier. One of that is the coining process, the coining where you make coins. So it is in fact a closed die forging process, and it implies using a very high load because of the high A by H ratio of the coin. No lubricant is used in coining. Okay, so the lubricant is not recommended because it can fill part of the die cavity and hinder the material flow in the fill of the die, and therefore there is no need of using any lubricant because the A by H ratio is very low. The another operation is heading, where you make heads of the bolts and rivets, etc. Third, very common, is the piercing, where you use a punch, which is as shown here in this figure. This punch is generally forged into a workpiece to form a cavity, which is shown here. So you look at the punch, is a workpiece, and this punch is pressing it, and then you create the and that's the bump cell, etc. I explained yesterday. Usually bump cells are produced with this. The hobbing is another very important operation where you make hubs like here, so which is similar to piercing, but the punch is at the center and is of a certain geometry where you make it. So the hubs are formed. Like this shows a rectangular cross section of the punch. Cogging is another example where the workpiece is rotated as well as. So the cogging involves successive thickness reduction. In fact, now you can look into. So the things are there. It is rotating the workpiece. You can rotate it like, and then there is a successive reduction in cross section. The roll forging is another very popular process in forging, where the cross sectional area of a bar is reduced and altered in shape by passing through a pair of rollers. Generally you can produce the taper shafts, pre-stages of a crankshaft like this. So you can see the arrangement of the rollers here. So the workpiece, the red one, and then how do you proceed. So this is what's the example of roll forging, where you make use of rolling and forging all together. The seventh one is skew rolling, where a very example for making round balls is the by way of skew forging, where you are using rolling of balls. So you can see here the stock which is rotating and the two rollers of that creates a different gaps, and then it passes through and finally it cuts the finished ball. So that's a very popular and interesting way, because when you produce balls by forging, the strength is very high and the flow lines and so all advantage of the forging, cold forging, you take it here, as well as the hot forging. This is the skew forging where you make bigger balls, so that's the hot forging case. As I told you, the cold forging is generally for a smaller load, smaller workpiece. So generally the forging temperature is important as for the different alloys, forging of different alloys are concerned. Generally aluminum alloy we come across the temperature range as 400 to 450 degrees centigrade. For copper alloys it is 625 to 950 degrees centigrade, whereas alloy steels, that is harder, and so we come across 925 to 1250 degrees centigrade. As you know, for all hot cases, generally cold case we do not use any lubricant, but when there is a hot forging uh, we use some lubricant so that there is a reduction in the die wear. There are cases where in even the cold case a little bit lubricant is used. So lubricant reduces the die wear, it affects the flow in the die cavity, and also it serves as a parting agent and prevents sticking of the forging while forging goes on, and also very important, it reduces friction, and as a result it saves energy. So generally we, in case of hot forging, the different lubricants we use, the graphite is very popular, molybdenum, glass pads, glass granules are also used in hot forging cases. For the cold forging lubricants generally it is used the mineral oil, water, soap, and all these are very popular lubricants. We will explain in detail later, but let us see the types of forging that we come across in presses we come across. If you look at this figure, generally hydraulic presses are very popular. So because the speed is low and uniform is constant speed with the hydraulic presses, and load is limited and cannot exceed a certain value depending on the pressure. So generally the hydraulic presses one can come across 670 mega Newton and all that, so very heavy hydraulic presses are also available. The second category which is very popularly used in forging is the mechanical presses. So mechanical presses where you have the limited stroke, it needs proper setting during closed die forging, since the stroke has to complete the whole operation, and these presses, no doubt it has a limited stroke, but the largest capacity as far as is concerned, it is less than the hydraulic presses. So hydraulic presses are very popular for their large capacity. Generally the mechanical presses, like you have a screw, cranks, eccentric clutch, these are very different types of mechanical presses. So we would further continue this lecture because there are many issues as far as the die design is concerned we would take up, and industrial issues also we would take up, the popular materials that, and other technological issues we will discuss in the subsequent lectures. So I thank you all for your patience for listening the lectures, and hopefully this today's lecture gives you an idea of the forging industry, the difficulties, the qualities that are concerned. So please give your feedback, don't forget to give your feedback. Thank you very much. Thank you.